Hello viewers, welcome to our YouTube channel Incredible Maths. In this video, we will solve a problem asked in CSIR NET June 2023. It's a part C question. So let us go into the problem directly. So given that V is a vector space of polynomials of degree at most 10 with real coefficients. So therefore, dimension of V is 11. So we know that if we set up all polynomials of degree n, then dimension of this Pn is n plus 1. So based on this, dimension of V is 11. And W1 is a subspace of V consisting of polynomials of degree at most 5. So therefore, dimension of W1 is 5 plus 1 is 6. So next we will write dimension of W2. It's a set of all polynomials such that sum of their coefficient is 0. So therefore, the dimension of W2 is 1 less than the dimension of P, that is 10, because we have one condition imposed. W2 is W is the smallest subspace consisting of both W and W2. So therefore, W equal to W1 plus W2. So this is the smallest subspace of V containing both W1 and W2. So now we will find dimension of W1 intersection W2. So what is W1 intersection W2? So this will consist of set of all polynomials of degree 5 and sum of their coefficients is 0. So therefore, a dimension of W1 intersection W2 is 6 minus 1, so this is 5. So now we will find dimension of W1 plus W2, that is dimension of, so this is nothing but dimension of W. So we have the formula dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So dimension of W1 is 6, dimension of W2 is 10, dimension of W1 intersection W2 is 5. Therefore, we get the answer as 11. So this is dimension of W. So already dimension of V is 11. So this implies, since W and V are finite dimensional vector space, so from this we can conclude that W is equal to V or V equal to W. Therefore, the second option is correct. The dimension of W is at most 10. So dimension of W is at most 11 here. Therefore, the first option is wrong. And the fourth option, dimension of W1 intersection W2 is at most 5. So we got dimension of W1 W2, W intersection W2 is 5. So therefore, this is correct. So now we have to check whether this option C is correct or not. So W1 is contained in W2. So let us take a polynomial, take an element in W1. So now we will check whether this element will be in W2 or not. So here, but x square is not in, so x square is not belongs to W2, because since sum of the coefficients is not 0. So therefore, W1 is not contained in W2. W1 is not a subset of W2. Therefore, the option C is wrong. So let us see one more problem. Let T from R3 to R3 be a linear transformation satisfying the condition T cube minus 3T square equal to minus 2y, or this can be written as T cube minus 3T square minus or plus 2I equal to 0, and I is the linear identity transformation. So we have to check the statements, given statements are true or false. The first option, R3 must admit a basis B1 such that the matrix of T with respect to B1 is symmetric. So given that this is a polynomial, so T is a transformation satisfying this polynomial. So let's write the polynomial. So it is T cube minus 3T square, it is plus 2y equal to 0. So let us find the roots of this. So x square minus 3x square plus 2 equal to 0. So this x cube. So we can easily see that x is equal to 1 is the root. So therefore we will do the synthetic division. So 1 minus 3, 0, 2, 1. So this is 1. 1 is 1, 1 minus 2. So here we get minus 2 minus 2, and 1 into minus 2 is minus 2, 0. So therefore the resulting equation is x square minus 2x minus 2 equal to 0. So when we solve, so we get x is equal to minus 2 is 2 plus or minus root of b square minus 4ac, so minus 4 into minus 2, so we'll get plus 8 by 2a, is 2, so finally we get 1 plus or minus root 3. So this is x. So therefore, so the x is equal to 1, 1 plus root 3, 1 minus root 3. So these are the roots of this equation. So since the roots are distinct, so we have distinct roots, so therefore, so this can be considered as the eigenvalues. So these are eigenvalues. Eigenvalues are distinct. So we can conclude that the matrix T is diagonalizable. So T is diagonalizable, then T is similar to a symmetric matrix, and T is also similar to the triangular matrix. So therefore, the option R3 must admit a basis B1 such that the matrix of T with respect to B1 is symmetric. So this is true since diagonal matrix is similar to the symmetric matrix, and also diagonal matrix is similar to the upper triangular matrix. So therefore this is also true. So next we will check the option C and D. R3 must contain a non-zero vector B such that TV is equal to B. So we will check whether this is satisfied or not. So suppose if we take T is equal to this matrix 1 0 0 0 1 minus root 1 plus root 3 0 0 0 1 plus root 3, then we have a non-zero vector. Suppose if we take V is equal to 1 0 0, then we will get TV is equal to V. Suppose if we take any other matrix T satisfying the given condition, suppose if we take T is equal to 1 plus root 3 0 0 0 1 plus root 3 0 0 0 1 plus root 3, then you cannot find a vector. So for this matrix, for T is equal to this one, So there doesn't exist V such that TV is equal to V. So therefore, for this matrix, okay, so again we can check that this matrix satisfies this condition, given condition. So therefore we can take this as V. So this matrix, for this matrix there exists no V such that TV is equal to V. So therefore the condition C is wrong. So and automatically the condition D will also be wrong. So here there exists no a single vector. So here we need to have two vectors. Therefore option C and D are wrong. So another important statement is, so given the characteristic polynomial for a matrix, for a given matrix, characteristic polynomial is unique, but for a given characteristic polynomial, we cannot find a unique matrix satisfying the given characteristic equation. So this is very important point. So we will see an example. Suppose if we take A is equal to 1, 2, 3, 0, 4, 5, 0, 0, 6. So here the characteristic equation is x minus 1 into x minus 4 into x minus 6 equal to 0. So for this matrix the characteristic equation is 1. Suppose if we are given the characteristic equation, if x minus 1, x minus 4, x minus 6 equal to 0 is the characteristic equation, then the matrix, so then the matrix A can be the same 1, 2, 3, 0, 4, 5, 0, 0, 6, or this one 1, 0, 0, 0, 4, 0, 0, 0, 6, or 1, 2, 0, 0, 0, so this is 0, 4, 5, 0, 0, 6. So there are so many possibilities, or even A can be 1, 0, 0, 2, 3, 2, 4, 0, 0, 0, 6. So therefore, for a given matrix, the characteristic equation is unique. But suppose if you are given a characteristic polynomial, then there can be more than one matrix satisfying the characteristic polynomial. So based on this result, so we have deleted the option C and D. So therefore, for this question, option A and B are correct. So if you like the content of this video, so kindly like and share with your friends. Also subscribe our channel for more videos. Thank you.